Good evening, students. For the last couple of days, we are discussing periodic properties. So, let us recall what we have discussed so far. The properties of elements which get repeated at regular intervals of atomic numbers 2, 8, 8, 18, 18, 32 are called as periodic properties. And this phenomenon is called as periodicity, and the atomic number intervals are known as magic numbers. There are a total of 9 periodic properties. Atomic radius, ionization energy, electron affinity, electronegativity, electropositivity, metallic and non-metallic nature, acidic and basic nature of oxides, valency, as well as oxidation state, diagonal relationship. So, what are these? How they change a long period? How they change down the group? What is the reason for such kind of variation? That is what we are discussing. So, atomic radius is defined as a distance from the center of nucleus to the outermost orbit of an atom. So, this atomic radius increases with the increase in the number of orbits, decreases with the increase in the nuclear charge. As per the definition, atomic radius cannot be calculated. Therefore, various terms have been introduced, like van der Waals radius, covalent radius, metallic radius, and ionic radius. Van der Waals radius is defined as half the internuclear distance between two atoms that are bound by means of van der Waals forces of attraction. It is applicable for inert gases in general. Covalent radius is defined as half the internuclear distance between two atoms that are bound by means of a covalent bond. This term covalent radius is generally used for non-metal atoms. Metallic radius, it is defined as half the internuclear distance between two metal atoms bound by means of metallic bond in the crystal lattice. So it is, as the name indicates, used for metals. Same metallic radius can be used for metalloids also. Ionic radius is further of two types, cationic radius and anionic radius. So, cationic radius is applicable for cation, that is positively charged ion. Anionic radius is applicable for anion, that is negatively charged particle. So, among these four types, van der Waals radius magnitude is the highest, followed by metallic radius, followed by covalent radius. Van der Waals radius is approximately 40% higher than that of covalent radius. Among the ionic radii, cationic radius is always less than that of atomic radius as well as anionic radius. And here, with increase in the magnitude of positive charge, cationic radius proportionately decreases. Whereas anionic radius is larger than corresponding cationic radius as well as atomic radius. With increase in the magnitude of negative charge, proportionately anionic radius increases. So these are three types of radii: van der Waal, covalent, as well as metallic. These values decrease along a period and increase down the group. Then ionization energy. Ionization energy is also known as ionization enthalpy as well as ionization potential. It is defined as the amount of energy required to take away the outermost electron from neutral gaseous atom. Ionization energy is related with atomic radius, as ionization energy is inversely proportional to atomic radius. So, with increase in atomic radius, ionization energy decreases and vice versa. Therefore, along a period, ionization energy increases, down the group, ionization energy decreases. Then, electron affinity. It is the reverse process of ionization energy, we can say. Amount of energy released when an electron is added to the outermost orbit of a neutral gaseous atom is known as electron affinity. Electron affinity is numerically equal to ionization energy with the change in the sign convention. So you can write like this: EA is equal to minus of IE. Then electron affinity is also inversely related with atomic radius. With increase in atomic radius, electron affinity decreases and vice versa. Therefore, just like ionization energy, electron affinity also increases along a period and decreases down the group. Ionization energy and electron affinity both have the units of energy. So either you can make use of joules or calories or kilocalories, depending on the system followed. Then electronegativity. It is the capability of an atom to attract the shared pair of electron more towards itself. So this electronegativity is also inversely proportional to atomic radius. It increases along a period and decreases down the group. The electronegativity is measured in two types of scales. One is called Mulliken's scale and second one is Pauline's scale. Mulliken's scale is not accurate, so Pauline's scale is in use, which is based on bond dissociation energy values. And Pauling has calculated electronegativity values of all other elements by comparing with the electronegativity of hydrogen, which is taken as equal to 2.1. The relation used is Xa minus Xb is equal to EAB minus half of EAA plus EBB power 1 by 2. Xa minus Xb is equal to 0.208 into square root of delta. In place of delta, you can make use of this relation: EAB minus half of EAA plus EB. So, the range of Pauling's scale is from 0 to 4, midpoint being taken as 2.1. Hydrogen is given the value of 2.1, highest value of 4 is given for fluorine. Second highest value is with oxygen, third highest is with chlorine as well as nitrogen. Carbon has an electronegativity of 2.5 on the Pauling's scale. So, by using the electronegativity values, we can calculate percentage of ionic character in a covalent bond. So indirectly, it will tell whether a covalent bond is having 100% ionic character or 100% covalent character or in between. In general, if the difference in electronegativity between two atoms is equal to 1.9, then it will have 50% ionic character and 50% covalent character. Exact percentage of ionic character can be calculated by using this relation. 16 into Xa minus Xb plus 3.5 into Xa minus Xb whole square. So, by using these relations, we can assess the percentage of ionic character. The electronegativity value increases along a period, decreases down the group. Electropositivity is the opposite property of electronegativity. Electropositivity indicates the ability of an atom to lose electrons. So, electropositivity is directly proportional to atomic radius. Along a period, the electropositivity decreases and down the group, electropositivity value increases. Then, this electropositivity and electronegativity, they also define whether an element is metallic in nature or non-metallic in nature. Metals have higher electropositivity value, whereas non-metals have higher electronegativity value. So, metallic character decreases along a period, increases down the group, whereas non-metallic character increases along a period and decreases down the group. So, if the values are in between, that element will be called as semi-metal or metalloid. In the periodic table, there are a total of 5 metalloids. Then, next property, acidic and basic nature of oxides. It is dependent on the previous property. Metallic oxides, they are basic in nature, whereas non-metallic oxides are acidic in nature. Semi-metallic oxides will be amphoteric in nature. Amphoteric means they can react with both acids as well as bases. So, as metallic character decreases along a period, basic nature of oxides also decreases. Metallic character increases down the group, therefore basic nature of oxides also increases down the group. Non-metallic character increases along a period, therefore acidic character of the oxides increases along a period and decreases down the group. So the amphoteric oxides, we have to remember, along with the semi-metals, few metallic oxides also act as an amphoteric in nature. They are aluminium, tin, lead, zinc, and beryllium. So these are all metals, but their oxides have amphoteric nature. So these are the special cases that we have to remember. Then valency or oxidation state. Oxidation state is equal to plus or minus valency. In the sense, numerically these two are same. Oxidation state indicates the charge, whereas valency just number. So this valency is defined with respect to hydrogen and with respect to oxygen. With respect to hydrogen, whatever valency we calculate, that is called as a minimum valency. Whereas the valency that is calculated with respect to oxygen will be called as maximum. So the minimum valency along a period increases from 1 to 4 and then decreases to 1. Whereas maximum valency along a period increases continuously from 1 to 7. In a given group, valency generally remains constant with a few exceptional cases that we have discussed yesterday. Then diagonal relationship. Among second and third period elements, diagonally placed elements have similarity in their properties. This peculiar behavior of elements is called as diagonal relationship, and the elements which show diagonal relationship, they are called as diagonal pairs. There are only three diagonal pairs. One is lithium, magnesium, beryllium, aluminium, boron, silicon. So, for these elements, polarizing power is equal, which led to similarity in properties. Polarizing power is calculated by means of this relation, charge by radius square. Whichever elements have similar polarizing power values will have similarity in the properties. So these are the various periodic properties. Out of the periodic properties, diagonal relationship is a limited property applicable for just three pairs of elements that are present in second and third periods and in the first four groups 1A, 2A, 3A and 4A. Then we were discussing various types of atomic radii. Today we will see what are the factors affecting the ionization energy values. Ionization energy. It is also called as ionization enthalpy as well as ionization potential. All mean the same. It is defined as the amount of energy required to take away one electron from the outermost orbit of a neutral gaseous atom. So theoretically, any element can have n number of ionization energy values, where n represents total number of electrons. So when you start removing the electrons one by one, the amount of energy required keeps on increasing proportionately, because initially atom will be neutral. So number of electrons and number of protons will be equal. But once you start taking away the electrons, number of protons remains same, but number of electrons present in the atom decreases. As a result, atom will acquire positive charge, and with increase in the magnitude of positive charge, attraction force between nucleus and electrons present increases. Therefore, successive removal of remaining electrons becomes difficult, or we have to spend more energy. So, if E1, E2, E3, so on, En are the various ionization energy values possible for an element, it is always En greater than En minus 1, E3 greater than E2 greater than E1 itself. Say for example, you take the case of lithium. In atomic state, lithium can be visualized as made up of 3 protons inside the nucleus, 2 electrons in the first orbit, and 1 electron in the second orbit. So, in this situation, the forces of attraction are in a balanced manner. So, from lithium, when you take out 1 electron, it will become Li plus unipositively charged ion. For this purpose, whatever energy is required is called as first ionization energy. And this lithium ion can be represented like this. 3 protons, their number has not changed, and number of electrons are 2. So, suppose from this unipositively charged lithium ion, you want to take out 1 more electron. Energy required will become IE2, second ionization energy. Now, IE2 value will be higher than IE1. And suppose from this dipositively charged ion, you want to take out 1 more electron. Then energy required will be called as IE3, third ionization energy. And for lithium, that is the possible number of ionization energy values. So, if you compare these ionization energy values, it has been observed that IE3 is greater than IE2, and between second ionization energy and first ionization energy, there is a lot of difference. IE2 value is far higher than IE1. So, what is the reason for it? Similarly, along a period, as you move from left to right, general statement what we give is ionization energy increases. But group-wise, if you analyze, second A group elements have higher ionization energy values than third A group elements. Similarly, 5A group elements have higher ionization energy values than 6th A group elements. And the ionization energy values of 0 group elements are the highest. So like this, wherever abnormal values come, we have to analyze them. So these anomaly values can be explained by means of some factors, what we call the factors affecting the ionization energy. The ionization energy of a species depends on many factors. They are atomic radius, nuclear charge, screening effect, also known as shading effect, penetration power, and stable electronic configuration. So, by taking into account all these 5 factors, we can predict the ionization energy value of a particular atom or a particular ion. So, let us see one by one. How atomic radius influences the ionization energy. So, in an atom, there is nucleus and there are specific number of orbits. So, there is always force of attraction operating between the nucleus and the moving electron. This nuclear force of attraction is calculated by using Coulomb's law. F is equal to Q1 Q2 by D square, where Q1 represents charge of the nucleus, Q2 represents charge on the electron, D represents distance between the nucleus and electron. So, here the force of attraction is inversely proportional to square of the distance between nucleus and the electron. With increasing d value, force of attraction proportionately decreases. That is why for smaller atoms, ionization energy value is higher, whereas for larger atoms, ionization energy value is less. So, based on this relation, what we can say that ionization energy is inversely proportional to atomic radius. That means with increasing atomic radius, always the nuclear force of attraction decreases, and as a result, ionization energy value also decreases. So, along a period, if you see, atomic radius decreases and down the group, atomic radius increases. That is why ionization energy value increases along a period and decreases down the group. In a given period, element belonging to first A group will have the smallest ionization energy value, whereas element belonging to 0 group will have the highest ionization energy value. Then nuclear charge. Nuclear charge refers to the number of protons present inside the nucleus. So, with increase in the number of protons inside the nucleus, the magnitude of nuclear charge increases. When magnitude of nuclear charge increases, nuclear force of attraction increases, and as a result, ionization energy also increases. So the relation between nuclear charge and ionization energy can be represented as ionization energy is directly proportional to nuclear charge. Then the next factor is screening effect or shielding effect. What is meant by that? Say for example, this is the nucleus. This is first orbit, second orbit, third orbit, let us say. Here one electron is present, here one electron is present, here one electron is present. So, which electron will experience maximum nuclear force of attraction? Is it electron present in the first orbit, second orbit, or third orbit? Obviously, we will say electron present in the first orbit will experience maximum nuclear force of attraction, and as this distance increases, the magnitude of nuclear force of attraction decreases. Now, question is why the magnitude of nuclear force of attraction decreases as we move away from the nucleus. For that, there are two reasons. One is distance is increasing. When distance increases, nuclear force of attraction decreases as per the Coulombic relation. So not only distance, one more factor also comes into picture. The between the outermost orbit and the nucleus, there are inner orbits and inner electrons. What these inner orbits and inner electrons do is they absorb the magnitude of a nuclear force of attraction. So indirectly, inner orbits and inner electrons, they are acting as screens or shields for the outer electron and outer orbit from the nuclear force of attraction. So this particular phenomenon is called as screening effect or shielding effect. With increase in the number of inner orbits, magnitude of screening effect increases. And when screening effect increases, ionization energy decreases. That means screening effect is directly proportional to number of inner orbits, and ionization energy is inversely proportional to screening effect. That is why, by considering screening effect and nuclear charge, another term called as an effective nuclear charge has been introduced. Effective nuclear charge can be defined as a difference between the expected force of attraction due to the magnitude of positive charge present inside the nucleus minus the influence of the screening effect or shielding effect. So, point is, with the increase in the number of inner orbits, screening effect or shielding effect magnitude increases, and when it increases, ionization energy proportionately decreases. Then, one more factor is penetration power. What is this penetration power? And how it will influence the ionization energy value. Say, this is nucleus and this is orbit. Suppose in the same orbit there is S sublevel, P sublevel, D sublevel as well as F sublevel. So, as they are all present in the same orbit, the distance from the center of nucleus to that particular sublevel will be equal. Then, energy required for the removal of electron from these subshells, will it remain same or will it be different? Practically observed phenomenon is energy required for the removal of electron depends not only on distance but the type of subshell also. This is because of difference in the shapes of these orbitals. So even though they are present in the same orbit, their relative distance from the nucleus differs due to difference in their shapes. And that phenomenon is called as penetration power. The order of penetration is S greater than B greater than D greater than F. That means always it takes more energy to remove electron from an s orbital compared to f electron. So this phenomenon is called as penetration power. Then last is a stable electronic configuration. Some of the configurations are considered to be more stable. So whenever we come across stable configurations, suddenly there will be increase in the ionization energy values. The stable electronic configurations are NS2, known as a doublet configuration. Then NS2 NP6, it is known as an octet configuration. N-1 D10 S2 P6. This is known as a pseudo octet configuration. Then D5 P3, these are called half-filled configurations. P6, D10, F14, these types of configurations are called fully filled configurations. So whenever we come across an element or ion with one of these configurations, their ionization energy value suddenly increases. Among various types of stable electronic configurations, octet configuration is the most stable, followed by doublet, followed by pseudo octet, then it is followed by fully filled, and it is followed by half filled. So whenever we come across these configurations, there will be sudden increase in the ionization energy values of the elements. For example, along a period, if you see 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A also called as 0. So here we are considering S and P block elements for the purpose of comparison. As you move from first year to 0 group, IP value increases, but not in a regular manner. The observed order is 1A followed by 3A, followed by 2A, 4A, then 6A, 5A, then 7A, and 0. So there is the difference in case of second A group elements and fifth A group elements. Their IP values are slightly higher than the next group elements. So the reason for this deviation we can explain based on the stable electronic configurations. The secondary group elements have NS2 type of configuration, which is a doublet configuration and is stable next to octet. So because of this stable electronic configuration, their ionization energy values are higher than expected. Similar exceptional case comes in case of 50A group elements. It is the electronic configuration is NS2NP3. So here what is happening, we are coming across half-filled stable configuration. So that is why the IP values of 5A group elements are higher than expected. And 0 group elements have the highest ionization energy, even though their atomic radius is slightly higher than halogens or 7th A group. So here also that difference can be explained by means of electronic configuration. 0 group elements have stable octet configuration. That is why their IP values are the highest. So generally speaking, in a period, element with the least IP value belongs to first A group, and element with the highest IP value belongs to 0 group. One more aspect what we have to see is in the examination they will give number of ionization energy values. From that, we have to predict the valency of that particular element. Let us take an example. The first ionization enthalpy values of the elements sodium, magnesium, and silicon respectively are 496, 737, and 786 kilojoules per mole respectively. Predict whether the first ionization energy of aluminum will be more close to 575 or 760 kilojoules per mole. The first ionization enthalpy values of the elements sodium, magnesium, silicon are 496, 737, 786 kilojoules per mole respectively. So, predict whether the first ionization enthalpy of aluminum will be more close to 575 or 760 kilojoules per mole. So, like this, problems will be given. Here, we have to see the relative positions. Sodium, magnesium, silicon, and aluminum. They belong to same period, that is third period. Group wise, if you see sodium followed by magnesium followed by aluminum and then silicon. Sodium value is given as 496, magnesium is given as 737, silicon is given as 786. Now, what is the ionization energy, first ionization energy of aluminum? Will it be nearer to 575 or nearer to 760? How to predict? We can make use of factors affecting the ionization energy. If you look at the configuration, sodium has an NS1 configuration, magnesium NS2, aluminum NS2, NP1, silicon NS2, NP2. And sodium belongs to first A, magnesium 2A, aluminum 3A, and silicon 4A. Magnesium, because of stable electronic configuration, its first ionization energy value is somewhat abnormally high. And aluminium should be having ionization energy which is less than magnesium. Therefore, the first ionization energy of aluminium must be nearer to 575 kilojoules per mole. Because of the stable electronic configuration, order of ionization energy values is slightly changed. The first IP of secondary group elements is higher than that of third group elements, and it is followed by fourth. So like this, when values are given, we can identify their relative positions. One more type of problems that we come across is here different elements are compared. Sometimes for the same element, different ionization energy values will be given. By looking at the ionization energy values, we have to identify the probable valency of the element. Say for example, some unknown element X has 100, 200, 300, 600, 700 kilojoules per mole of successive ionization energy levels. Successive in the sense, say this is IE1, IE2, IE3, IE4, IE5. So, by looking at these values, predict probable valency of the element X. Like this also problems may come. So here 100 to 200 means increase in value but not abnormal. That means removal of second electron is not taking much effort. Similarly, IA3 300 means that is also along in line with the increasing IA2 value. But 300 to 600 means it is an abnormal increase. That means energy required to take out fourth electron is very much high compared to the energy required for the removal of third electron. Then next what is happening, this increase is again normal. That means at this particular position that atom is having stable electronic configuration. Therefore, the stable valency of the element can be taken as equal to 3. So like that, wherever abnormal increase comes, there you can assess that that atom is getting or it is coming across a stable electronic configuration, and from that we can predict the number of valency electrons. So these are the types of problems that you may come across. Clear? So that is what we about periodic properties and their variations. Based on this concept, whatever we have discussed so far under the heading of periodic properties, if you have any doubts, you can ask now. Thank you. penetration. One of the doubt raised is regarding penetration power. So suppose this is the nucleus and this is an orbit. In this orbit, there is S, P, D as well as F sub. So it appears that these are equidistant from the nucleus, but they are not exactly equidistant because of difference in their shapes. So, because of that difference in the relative distances of sublevels that are present in the same main energy level, there will be difference in the energy levels required to take out electron from those sublevels. That phenomenon is called as penetration power. The order of penetration is S greater than P greater than D greater than F. That means it is always difficult to take out an S electron and easy to take out F electron because of a difference in their shapes. S is a spherical, that is a symmetrical structure. P, D and F, they are not that much symmetrical. That is why energy required to take out electron from these suborbits differs even though all are present in the same orbit. So that phenomenon is known as penetration power. And one more question raised is, in what way ionization energy and nuclear charge are related with each other? So ionization energy is directly proportional to nuclear charge. Nuclear charge actually represents or refers to what number of protons present inside the nucleus. So between the nucleus and a moving electron, always there will be two types of forces operating. One is the nuclear force of attraction and one is the tangential force due to movement of electron. When these two are in balanced state, electron will be moving in a particular orbit at a fixed distance. So the nuclear force of attraction is calculated by using this relation Q1 Q2 by d square, where Q1 stands for charge of nucleus, Q2 charge of electron, d distance between the nucleus and electron. So when distance increases, force of attraction decreases. When magnitudes of charges increase, force of attraction increases. So when there is increase in the number of protons present inside the nucleus, nuclear charge magnitude will increase, which in turn increases the nuclear force of attraction proportionately. And when force of attraction increases, energy required to remove that electron will become more, or ionization energy value also increases. In that way, nuclear charge can influence ionization energy, and the relation is ionization energy is directly proportional to nuclear charge. So, how to calculate oxidation states? This concept actually we practice in basic concepts of chemistry. Oxidation state can be taken as equal to plus or minus valency. That means valency is just combining capacity, it is a number, whereas oxidation state corresponds to type of charge acquired by an atom during the formation of a compound. More electropositive elements get a positive value, more electronegative elements get negative value. So here the concept is known to unknown. The oxidation state values of some elements, we consider them to be known, and by using those values, we will calculate the unknown. So, common valency values of elements, yesterday we have discussed. So, using those values, we will calculate the unknown values. For example, the valency of first A group elements is always 1. That means oxidation state of any first A group element is always equal to plus 1. Why? Because first A group elements are electropositive metals. And for electropositive elements, oxidation state will become plus valency. So, for example, you take the case of water. Here, what is the oxidation state of oxygen? Suppose you want to calculate. So, the type of elements involved here are hydrogen and oxygen. If you check the electronegativity values, hydrogen electronegativity is 2.1, whereas oxygen is 3.5. That means oxygen has a higher electronegativity, hydrogen has a lower electronegativity. Therefore, oxygen will have negative oxidation state, while hydrogen will have positive oxidation state. Hydrogen belongs to first A group. Therefore, each hydrogen will carry plus 1 unit of charge, we can say. So, into 2 plus oxygen, we want to calculate, say, X. And sum of the oxidation states in a molecule is always equal to 0. So, from this, X value comes out to minus 2. That means oxidation state of oxygen in water is minus 2. But if you carefully observe, the valency of oxygen is 2. If you consider the electronegativity being more electronegative, oxidation state means simply you can put negative sign followed by valency value. So like this you can calculate, like this also you can calculate, and there are number of examples in the topic basic concepts of chemistry. Once you can go through it, and if you get any doubts, you can come back always. Cl servo H2O taken 5 times plus 2. So, one of the question raised is whether oxidation state and covalency of aluminum are they same or are they different in this species. The species represented in this example is called as a complex ion. So here two different things are involved. One is valency and second one is covalency. Valency refers to the combining capacity of an element with the other elements. It is calculated with respect to hydrogen and with respect to oxygen. And depending on the electronegativity value, valency, if we give sign, it will become oxidation state. Whereas the term covalency refers to number of covalent bonds developed by an atom in a chemical species. So first let us check covalency. This is complex sphere or complex ion. Aluminium is called as a central metal atom. Here it is in combination with one chlorine atom and five water molecules. Therefore, these things in complex ion are referred to as ligands. Each ligand can develop one dative bond, coordinate covalent bond with the central metal atom. Coordinate covalent bond is considered as a special case of covalent bond only. Therefore, here aluminium has developed a total of 6 covalent bonds. So, covalency of aluminium in the compound is 6. Now coming to oxidation state. Chlorine is a uni-negative ligand. Water is a neutral ligand. So suppose X is the oxidation state of aluminium plus chlorine oxidation state, we have to take -1 plus 5 water molecules are there, but each water molecule carries no charge, 0. In case of ions, the sum has to be equated to charge, that is +2. From this, x minus 1 is equal to, we can write +2, or x value comes out to +3. So this corresponds to oxidation state. So oxidation state of aluminium in this chemical species is +3, whereas covalency is 6. Okay. So one of the question raised is screening effect. This screening effect is also called as a shielding effect. So to understand this concept, let us take the example of classroom itself. Suppose this is nucleus. In place of nucleus, imagine the teacher. And before the teacher, students are sitting in various benches, number of benches. Say first row, second row, third row, fourth row. Which student can hear the voice of teacher clearly? Student sitting in the first bench or student sitting in the fourth bench? Obviously, answer is first one. Why it is like that? Distance between the teacher and the student is the least. Therefore, there will be clarity of voice. Then, when it comes to last bench, clarity decreases because of two reasons. One is sound is nothing but a form of energy. When distance increases, there will be loss of energy. That is why the intensity of sound will be less on the last bench. Not only distance, the inner benches and students sitting in these benches, they also act as absorbers of energy. As a result, the intensity of sound waves reaching the last bench further decreases. So, in one way, what we can say, the inner benches and inner students, they are decreasing the intensity of a teacher on the outermost bench. So, in this way, inner benches and inner students are acting as what? Screen or shield. to the outermost bench and outermost student from the influence of teacher. This effect itself can be taken as a screening effect as well as a shielding effect. With increase in the number of benches, inner benches, the decrease in the intensity further increases. So now apply this concept to the case of an atom. Nucleus, orbits, in place of students visualize electrons. The nuclear force of attraction is maximum on the first orbit and electrons present in the first orbit because there is nothing in between. But if you take the outermost orbit, between the nucleus and outermost orbit, inner orbits come, inner electrons come, which absorb the nuclear force of attraction effectively. As a result, the nuclear force of attraction on the outermost orbit and outermost electrons is drastically reduced. That phenomenon is called as screening effect or shielding effect. So the screening effect or shielding effect is directly proportional to number of inner orbits. And ionization energy and screening effect, they are related in this manner, inversely related. Clear?